My name is Hideki Koike from Institute of Science Tokyo, and thank you, Kasahara Sensei, for inviting me as a guest speaker in here. I'm very glad to be here. So, today's title is Skill Acquisition and Transfer System with AI and XR for Augmented Human. And first of all, our university recently merged to the medical university, and we changed our names from Tokyo Institute of Technology to Institute of Science Tokyo. So there are many struggles of changing the names, but finally, this is the decisions of our president. Anyway, so today's talk is just like this. So first, I'd like to talk about the introductions, and then I'm going to talk about the technologies for human augmentations we have developed. And after that, we will describe some application systems using such technologies. And finally, I'm going to talk about the skill-based economic systems we are currently working on. So first, the introductions. So as you know, there is a difficulties in skill transfer systems because, for example, athletes or music performers or handicapped persons have some kind of skills, very special skills, and we want to copy that technology, that techniques from one person to another. But there is a very difficulties to copy and paste such techniques from one person to another. So first of all, there is a limitations in measuring environment for such technical skills. For example, if you see those motion capture systems or gaze tracker systems, those equipment will limit the freedom of motions of those athletes. And also, there is another difficulties, that is most of the traditional skill acquisition systems do not have the real-time feedback to learners. So this is an example of the golf training systems. So this captures the motion of the golfers and then feedback the pose of the golfers, but this is not in real time. So this slide shows the overview of our project. So we want to acquire the skills from top athletes or expert musicians or people with disabilities. And then we want to make kind of the skill databases. And after that, we want to transfer those skills from those top athletes to ordinary persons by using AIs and VR and AR and some robotics systems. And this slide shows a process in the brain of acquiring motor skills. So this is a very famous figures from the papers. And usually there is the person is here, and in his brains, he has some kind of estimated state of the motions, but this is a desired state. So here is errors of this motion and this motion. And then based on these errors, he will give some feedback to the muscles to change his motions. So this is a very traditional the motor skills processes. But we think this, here is some desired skills he thinks right now. But usually those mental models has some differences between the real pose of these persons. So we want to externalize those mental models in the real world by using AR and VR, and we want to show the real errors from between his ideal state and his real state by using AR and VR. So this is a kind of process we are thinking about. And before we go into some details of our technologies, I want to talk about the democratizations of skill acquisition systems. So this is the present situation of the motion capturing systems. So here is a user. Usually this user is a very special person, some expert athletes or expert music performers or something like that. And then we need a very high cost sensing technology such as motion capture systems. It costs about 1,000 yen in Japanese. And based on this, the observations, the human coach will give some advices to the athletes. And because the number of users is very small, so there is a very limited number of data sets. But if we can reduce the cost of motion capturing from this 1,000 yen to, let's say, 10 yen or so, lots of number of people can capture his motions freely. And then it's going to make this database bigger and bigger. And those data sets can be used to teach the AI systems, I mean the deep learning systems. And then we could give much more scientific coaching from the AIs to those ordinary persons, not the special expert. So this is our ideal futures. So that's why I'm currently trying to make a very inexpensive motion capture technologies by using low-cost sensors. So I'm going to talk about some technologies we have developed. So first one is a 3D head body pose estimation using a chest wound camera. And so this is the background of our project. So as I described, this is a normal motion capture systems. It costs very expensive cameras and expensive PCs or something like that. And also, if we want to capture the gaze directions, we want to ask the users to wear those gaze trackers. So, but please think about, so this is a scene of the ski racers. So we attach this very small camera to his chest. And in this kind of very open environment, those traditional motion capture system doesn't work. And it is also very difficult to attach those wearable gaze sensors. So this is our prototype of motion capture systems just by using one camera, which is attached on our chest.
We present Mono-Eye, a multimodal human motion capture system using a single wearable device. The user simply wears a portable chest-mounted camera to use the system, and also it doesn't require any markers or calibration procedures. The ultra-wide fisheye lens of our hardware setup has a 280-degree field of view and can capture the user's limbs.
Oh, sorry.
We present Mono-Eye.
So this is a
environment. We realize a multimodal motion.
This is camera images from the chest wound camera. So since we are using very ultra fisheye lens cameras, so we can capture the images of the front image as well as a part of his body. So as you see here, here is the hands of this wearers, and also here is the hood of the wearers, and also his chin can be seen from these cameras. And please notice, this camera does not capture all the perfect information of the human bodies. So this information is very, how can I say, imperfect informations. But our system can estimate the human motions by using those imperfect informations. So here, this heat map shows the estimation position of the joint by using deep learning. And here is the estimated pose of the users.
With these methods, our system enables accurate motion capture with a portable wearable device.
And also,
estimates the user.
As I told, that this camera will capture the part of the face. It means chin or the face. So by using this very small images, the system also can estimate the head poses.
Estimates the user's head pose from a lower face image captured by the chest-mounted camera. We can crop the user's viewport from the ultra-wide fisheye image using the estimated head orientation and the neck position.
So this estimated viewpoint is estimated by using our technologies, and this actual viewpoint is captured by GoPro cameras, which is attached on the head.
First-person view capture. This rich information can be utilized in many end-user applications.
So this can be used for simply motion captures, and also some kind of the video logs of the users. And more importantly, if you are very familiar with deep learning technologies, it is very important to collect the data set of the images. But since our camera is our original and it's very unique, so there is no data set in the world. So that's why we have to make a very large data set using the ultra-wide fisheye lenses. So in order to do that, we generated the synthetic data set by putting the virtual human in the virtual environment. And then we changed the size of the virtual humans as well as the background of the virtual environment, and also the position of the cameras as well. And by using some augmented technologies, we developed a very large number of synthetic data set. So our deep learning system will learn from those synthetic data set, and it will show a very good estimation results. If you are very interested in the evaluations, please refer to our papers, but currently the MPJP is a mean per joint sorry, I'm currently very nervous. And MPJP is 43.6 millimeters in average, but by using a real world data set, it's going to be 84.9 millimeters. It is not enough for the capturing the athletes, but it might be allowed to capture the motion of the normal users. And in addition, our current system will estimate the motions, and its MPJPE is around 20 millimeters. So, and since our camera is faced on the front, so not only capturing his motion, but it can also capture the motion of the third persons in the front. So by using the normal motion capture technology such as open pose or something like that, it is very easy to capture the motion of the front users. So here is a result of the motion capturing. So this is a future concept of our technologies. So since the camera is getting smaller and smaller and lighter and lighter, so it could be used it would be embedded inside the pendant or tie pins or buttons in the future, in the very near future, I think. And by doing this, we can capture our motions of our daily life, not only the expert athletes, but also the normal persons. So next technology is the 3D hand finger pose estimation using wrist-worn cameras. So this is the overview of our technologies. So let me show you the background of our research. So currently the gesture recognition is getting popular and popular. And for example, we can use the gesture control for the home appliances, or we can use the gestures in the virtual realities. And but the problem is the current gesture recognition technologies need us to show our all fingers to the cameras. So if you want to make your gestures, you have to go in front of the cameras to show your gestures. So that's the problems of the traditional technologies. So that's why we have the cameras here, and he's showing the gestures on top of these cameras like this. And if the home appliance has the cameras, you have to show your fingers in front of the cameras, something like that. But we succeeded to capture the motion of the hand and fingers by using only the images of the back images of the hand. So we are currently considering to put the cameras at the position of the crowns of the smartphones. So if we put the cameras, very small cameras on the crowns, we can capture the images like this. This is a camera view from the crown's camera, the cameras at the crown positions. So by using these images, we succeeded to estimate the 3D hand poses in real time. So even in a very dark environment, our system can estimate the hand poses in real time. And also in the very bright conditions, it can also estimate the hand finger poses very precisely. So this is the architecture of our deep learning technologies. And so here is the evaluation of our methods. So currently, the error of the angle of the joint is less than 10 degrees. So you might think the 10 degrees is very large, but the state-of-the-art technologies just succeeded at the 15 degrees or 16 degrees before technologies. So we think it can become smaller and smaller near the futures. And if I talk this research to the persons in some industries, some researchers always ask me, oh, this is a very good technologies, but it's going to take a very long time to develop such smartphones, but it is not. For example, if you Google or if you going to the AliExpresses, you can buy Android-based smartphones less than $100 US, and it has a very small cameras at the position of the crowns. So by embedding our softwares inside this Android smartphones, we can do the same thing by using our technologies. So the third technologies is soft exoskeleton globe using pneumatic artificial muscles. So this is a kind of application of soft robotic systems. So this slide shows the soft exoskeleton globes we developed. So if you see this white thin string is pneumatic artificial muscles. So if you put the airs inside this artificial muscles, it will reduce its length 25%. So it's going to be an actuator of the robots. So we put the 4 pneumatic artificial muscles on each finger. Then it means so we have 20 artificial muscles on one hand. So this could be used to show the, to teach the pose of the hand by using this artificial muscle soft exoskeleton globes. So this is a joint work with Dr. Furuya of Sony Computer Science Laboratory, and he's an expert of the piano science of piano. So we compared those traditional hard exoskeleton globes and our soft exoskeleton globes. So we asked expert pianists to wear these 3 soft exoskeleton globes and then did some experiments. And the result shows most of the expert pianists likes to use our soft exoskeleton globes because it is very light and it does not limit their motions. And most importantly, or more interesting point is we asked the expert pianist to hit the keys as fast as he can before our experiment. Then we asked them to wear those our soft exoskeleton globes, and the soft exoskeleton globes force them to move their fingers much faster by himself. And after he take off his gloves, his hand moves faster before the experiment. So this is very interesting. So that Dr. Furuya said that those soft exoskeleton globes could be used for make the humans much stronger and or much more, not intelligent, but much more stronger, much more faster. And also we found a very interesting result in the experiment. So we asked them to wear the gloves on, for example, in his right hand to hit the keys faster. After the experiment, his right hand moves much faster than the experiment, so as I told. But his left hand moves also faster after the experiment. Do you think this is very interesting? So we don't know why, but Dr. Furuya has some hypothesis that there is some kind of bypasses between left brain and right brain. So if he moves his hand faster, it's going to be some signal in his left brain, and it will also transfer to his right brain, and it makes his left hand moves faster than before. But this is just a hypothesis, and we don't know why. So this is some kind of demo videos. So the soft exoskeleton group just teach when he hit the keys, not the positions. So this pianist has to remember the positions of the keys, but the system will teach when he hit the keys. So we also use this soft exoskeleton globes for some kind of rehabilitation purposes with the researchers in Keio University. And this is inspired by a mirror therapy for after effects of strokes. So this is a traditional images of the mirror therapies. So his left hand doesn't move because of the stroke, but he is seeing the virtual images of his right hand by using the mirrors. And then this is a kind of therapies. And by using this therapies, his left hand will move a little. So this is a very traditional technology. So inspired by this mirror therapies, we developed those prototype rehabilitation systems. So this patient will wear our soft exoskeleton gloves on his left hand, and he is wearing the kind of data gloves on his right hand. So if he moves his right hand, so that position of the hand and fingers will be transferred to this soft exoskeleton gloves, and he could move his hands. So here is some experiments. So since there is a very long time after he had his stroke, so his left hand becomes very solid. So it is very difficult to move his hand freely. But after the interviews, he told us that it will have a kind of potential for rehabilitation technologies. And after the strokes, it is better to use those rehabilitation systems much faster, just after the strokes. Okay, so I'm going to talk about the application systems very briefly. So first one is alpine skiing. So we are currently transferring the techniques of the top alpine racers. And then we want to make a data set of the alpine race ski data set. So here is images. So here's a former World Cup racers of Japan, and this is 3D motion capture images, and this is the insole sensors pressure information. This is a signal from EMGs, and so we are going to capture those information and then compare each athletes from the viewpoint of the poses as well as the insole, the pressures and also EMG signals. So the reason why we are doing this research is, so it is very difficult to capture the motion of the skiers because the ski slope is very wide and the condition is very different in each day. And even the same person performs differently on the same ski slopes. So that's why we try to introduce those indoor ski simulators. So she's Miss Michaela Schifrin. So she's the queen of the alpine race, and she's the fastest. And we put the motion capture systems around this indoor ski simulators and using insole pressure sensors and EMG signals. And then we are collaborating with Japan Institute of Sports Sciences, and this organization is for trying the Olympians or top athletes of Japan. So here is some images of the young athletes. So we capture the images, and by visualizing their motions, we advise them to what is the difference between him and top racers. So after capturing those motions, we also developed some VR ski systems. So we developed the VR ski systems like this. So this is a very small version of a ski simulator. And he's wearing HMDs. And so this is a motion capture process. And then he is seeing the motion of the top athlete in front of him. And then he wants to imitate the motion of this top racers just after him or her. So we will also shows the differences of the angle of the legs or pressures or something like that. Okay, and we also currently developing the ski system, VR ski systems for visually impaired persons. And we want to give some audio feedback to the person with visually impaired and visually impaired person. And our final goal is to capture the environment images by using chest-on camera, and then detects the obstacles or humans in front of him or around him, and then give some sound feedback by using headphones to him or her to ski safely. So, but it is very difficult to do this experiment in the real ski slopes because they need the volunteers who can ski with him or her. So that's why we use those ski simulators to train the person with the visually impaired. So this is the images.
Allow ski training all year round without seasonal or environmental restrictions. However, it is difficult for people with visual impairment to use a ski simulator, as the ski simulation system is designed only for sighted people. Skiing for visually...
Okay, let me skip this slides. So this is a golf training systems. So if you're interested in golf, so let me show you the big videos. Oh, here. Okay. So one of the difficulties of learning golf is it is difficult to know the current swing trajectories or positions in real time. So that's why we show such informations in real time on the floor just by using projectors. So as you see here, so if he swings the golf clubs, it will be shown on the floor the trajectories of the golf clubs and also the pose of his motions. The reason why we use the floor as a screen is the golfer has to focus on the balls. So he has to see the balls by using his central visions. And by using a peripheral visions, he can see his body poses and club trajectories like this. So this is some kind of typical visualizations of the graph trajectories. So this is the outside in trajectories. So this is the neutral trajectories, and this is inside out trajectories. And most of the beginners of the golfers, I heard that 70% or 80% of the novice golfers has this outside in trajectories. So this is cut trajectories. So that's why the ball is going to the right because the ball is spinning. So anyway, so finally, I'm going to show about some AI systems for the golfs. So since it is very difficult to teach what is the difference between the top golfers and novice golfers, so we want to use AI technologies to identify what is the difference between the top golfers and the novice golfers. So, but the problem is, since the freedom or degree of freedom of the human's motion is very large. So for example, in case of the joints, we have 17 joints to track the motions, and each joint has 6 degrees of freedoms. So it is very difficult to tell which part is the most important point to fix. So that's why we use AI technologies. And then we will show the swing images to the AI systems, and the AI system will compress that such large number of degree of freedoms to very limited latent spaces. And then we compare the differences between novice and the top golfers in the latent space. And if we find very large differences like here, we will decode these motions to the images. Then we can tell the novices which part is the most important point to fix. Okay, so here is this is the top golfers, and this is novice, this is me, and the AI system will compare those two golf swings, and by analyzing those golf swings, the AI system will can tell us which part, for example, the addresses or backswings or top positions, which part is the most important to fix. Okay, so let me skip this. So finally, before I'm going to the summary slides, let me talk about the skill-based economic systems. So as you know, the YouTube is very popular currently, and YouTube is a kind of economic systems based on the consumer-generated videos. So because of the cost of the camera becomes much and more inexpensive. So the normal people can capture the videos very freely, and then can easily upload the images to some kind of servers, and it becomes a kind of economic system. So by inspired these systems, we are currently very interested in developing a skill-based economic systems. So if we can develop the low-cost motion capturing systems, so normal people can capture these motions just as capturing the images by using low-cost cameras. So then they will upload such skill data to the skill data center. And some people who are interested in such skills can download that skill data. And then it's going to be a kind of economic systems. For example, if someone downloaded the skill data set, then he will pay very little money to the servers, and then the person who uploaded such skills will get some affiliations. Okay, so this is a summary of my talk. So I'm going to talk. I talked about the background of our researches and the fundamental technologies such as 3D body and head pose and finger and hand pose estimation technologies. And I talked about the alpine ski, golf ski, and since I didn't have enough time, I couldn't talk about the piano training systems, table tennis systems, and surgical training systems, but we did lots of skill transfer systems right now. So if you're interested, please ask me after this presentation. So thank you very much.